Okay, so today we will continue to talk about first law of thermodynamics. Before we do that, let's revisit an equation that I wrote last time, which got many of you thinking, which is regarding this degree of freedom and how it connects to the internal energy. So let's revisit that equation. So what we wrote last time is that U, the internal energy, is every degree of freedom contributes half multiplied by Boltzmann constant multiplied by temperature degree of freedom. So if you have a system with n degrees of freedom, the internal energy will be n number of degrees of freedom multiplied by half times multiplied by kT. This is all good. The problem happens in calculating n degree of freedom. How much is that? So let's try to look at it systematically. Let's make a small table and let's think about the number of degrees of freedom that we will have there. And finally, the energy. So the first system is an ideal gas made of n point particles. What will be the number of degrees of freedom for this system? It's in a three-dimensional box. Go ahead. N of them.
N times
3.
Yeah.
So 3n, right? Every atom can move in X, Y, and Z, and every atom can move independently of each other. So what will be the U? The U will be 3n divided by 2 multiplied by Kb multiplied by temperature. Let's move on to an ideal gas with n atoms. Okay, now look at the difference. What I'm saying, there are n atoms comprising, maybe comprising is the wrong word here, but you get an idea, molecules. Okay, so you still have n atoms like in the last case, but they are not independent. So in this case, you have some. So this is 1, 2, 3, 4, 5, 6. So this is 6 atoms, for example, but they are forming some sort of bond, okay? And the bond could be more complicated. The bond could have been something like this. In this case, what would you expect the number of degrees of freedom to be? So, okay, I'm not asking you to think too hard. I'm asking you to think just a little bit hard, okay? I'm not asking you to give me the exact number. I want you to tell me whether the number of degrees of freedom will be less than 3n, equal to 3n, or more than 3n. Why more? Who said more? Why do you think it will be more?
The molecule bond length and
It looks like it should be more, right? But if you think carefully, it will actually be less, because whatever bond length you are talking about changing, that's already accounted for in the atoms just moving, right? If in the box you had atoms like this, and if they were all moving freely in X, Y, Z, the bond length move that you're talking about is already accounted for in this. So by imposing a structure, you are definitely going to reduce the number of degrees of freedom. How much it reduces by, that's harder. You have to think about it carefully. Okay, but it will reduce, because what you're talking about, okay, I have this other degree of freedom, right? But what I'm saying is that this degree of freedom is already accounted for, that the atom could move in 3 different ways. So it's already accounted for. So in the second case, it will be definitely lower than 3n. How much will it be? That's something, you have to look at molecules, you have to compute it specifically. Oxygen will be different from helium. You have to look whether you are thinking about close to low temperature or higher temperature. Does quantum mechanics play a role or not? It becomes messy. But the thing to keep in mind is, we are still talking about an ideal gas, okay? So in this case, even though it will be less than 3n, it will still be proportional to n. For any molecule that you go and calculate it, it will still be proportional to n. This is quite important if it's ideal, which means that this thing over here will be proportional to n multiplied by Kb multiplied by T. The proportionality constant won't be 3 by 2, it will be something else. And once you do it for Generic molecules, you will see proportionality constants that sometimes look like 5/2, sometimes look like 7/4, etc. There are different proportionality constants depending on how many degrees of freedom you have. In the next homework, I will give you some examples where I won't be judging you for calculating the number of degrees of freedom, but I would like to use them to calculate something. However, I will point out material to you where it is demonstrated how to calculate the number of degrees of freedom. The thing to keep in mind, if it's ideal, the number of degrees of freedom is going to be proportional to n, okay? One way or the other. In both above cases, U of the full system is proportional to n and it's proportional to t, okay? Let's go to a third case now of a real gas. So the thing about ideal gases is they don't talk to each other, right? Molecules don't really chat with each other. In a real gas, we have interactions happening between different molecules. In this case, calculating the number of degrees of freedom becomes complicated. It's not easy. And most importantly, not proportional to n. It could depend on the volume, it could depend on the temperature, it could depend on the number. We know in general, anything can depend on P, V, T, N, right? We know that because that's the 4 variables that we need to characterize the system of the state of a system. But we also know that 4 reduce into some 3. So we could write it down as VTN, right? We could replace the pressure as a function of these 3. So we get VTN. So in this case, U will be a function of VTN, and it's hard to calculate. So this is something to keep in mind. It will show up today a little bit, but it will especially start to matter when we get into heat capacity. And a lot of students get problems related to heat capacity wrong because of this confusion. You assume everything is ideal. And then the internal energy becomes a very simple function. In fact, now if I ask you for case system 1, if I ask you to calculate the partial derivative of U with respect to volume at constant temperature, how much will it be? Who said 0? Why?
It's not dependent.
There is no volume dependence, right? It's 0. How much will be partial derivative of U with respect to temperature at constant V? Anyone else? No one? Go ahead. It will be 3/2 NKB, right? So you can calculate all these things. System 2. What will be partial U by partial V at constant T? There is still no volume dependence. It's proportional to something else, but there is no volume dependence. If it's ideal, this thing is still 0. When you go to system 3, partial U by partial V at constant T is not equal to 0. Later, we will see that this thing is called the internal pressure of a gas. So the ideal gas does not have any internal pressure. This internal pressure is different from the pressure exerted by, felt by the walls. So I'm showing you these partial derivatives because, we are ramping up the number of partial derivatives that you are going to see on a daily basis. If we plot it, August, September, October, November, December. And this is 0, and this is some very large value, infinity. It goes like this. This is you currently. This is you currently feeling like, yeah, it's not too bad. And soon, it might be very much like this. So be very careful with your partial derivatives. Do them. Try to do like 5 minutes of partial derivatives every morning when you brush your teeth, okay? That's my advice. I'm trying to learn Python and PyTorch. That's what I kind of I also do. I just wake up and go like, okay, I got to code Python for 30 minutes. Otherwise, it just becomes too much. Okay, so with that in mind, we are going to come back to this. This page is important. Go ahead. I don't think so. I don't think it cannot be.
Okay.
You might prove me wrong. If you find something, post on Slack, but I don't think so.
The real gas also are less.
Degrees of freedom, the presence of relations in a system are always constraints. I can give you a simple analogy from life. When I was single, I would just go around everywhere hanging out. Now I'm married, and my wife and I, plan our days together. So the number of degrees of freedom we have cannot really increase, right? Anytime you add a constraint on a relation, on a system, it cannot increase the number of degrees of freedom. It can only bring it down. Okay, so let's go to our first law of thermodynamics. So first law of thermodynamics is all about change in du, right? And we said that u is a state function. So the change in u can be written as an exact derivative d, but heat is not a state function. So the change in heat is going to be d cut q plus d cut w, also often written as delta q plus delta w, okay? Because these are inexact derivatives. So for those of you who joined late, I talked a little bit about how the potential energy, how the internal energy of a system depends on the number of degrees of freedom for ideal gases made of point particles, molecules, and real gases. And I showed some partial derivative properties. If you missed this, we will come back to this later, but it's good to show it once in advance already. And then the thing very much important to keep in mind, as this is the heat given to the system. This is the work done on the system. So if you're heating a system, delta Q is going to be positive. If you're cooling a system, delta Q is going to be negative. And this is something on which students get tripped sometimes. If you see delta Q is equal to negative, you go and change your first law of thermodynamics definition and everything becomes screwed up. Some books will write this as delta Q minus delta W. I think it's 50-50 of the books who change this, which is very confusing for students. But then it's not work done on the system. They are defining it as work done by the system. And this is a traditional difference that exists. We will follow this convention. So we talked a little bit about U. We showed how it's very easy to calculate for an ideal gas. It's almost boring. Let's talk about delta W, the work done on a system, how to calculate it, what does it really mean? And then after that, we will talk about the heat given to the system. So let's talk about work. So the work done on a system can be of different types. The simplest work done that one can think about is expansion work. So expansion work done on system. So you have a system and you have some surroundings, and the system is trying to expand, or the system is trying to contract. The surroundings are contracting the system. The formalism, even though we call it expansion work, it applies to contraction work also, okay? It's just like the sign changes. So the expansion work done on the system can be defined mathematically as what is work? Anyone remembers how do we get work from force? Force times distance covered, right? Force multiplied by distance. So this is going to be force external, which is a vector, multiplied by the displacement on the system. You integrate it depending on how long did the process went, and you put a minus sign. This minus sign is what allows this all to work. So we will develop a bit of intuition into this equation, how it looks like. So this is the net work done on a system. So what can we talk about the differential work done on a system? Delta W is going to be minus Fx multiplied by ds. So now let's assume a simple case. For now, let's assume for now that Fx and ds are along the same direction. Okay, so we are thinking about a system. This is our system, and we have some Fx applying vertically, and we have some change in displacement that is also going to have vertically. We are ignoring the motion that can happen along side A and B. Okay, so it's a very narrow tube. That's just an example that we are considering. It's easy to generalize it. So in this case, delta W can be written as minus Fx multiplied by ds, right? We don't have to worry about the vectors because we are thinking about things in the same direction. This thing, if the area of this thing is A, okay? Area is equal to, let's just call it area. If the area of this thing is area, this can be written as minus Fx divided by area multiplied by ds multiplied by area, right? I have done nothing profound. I have just multiplied and divided by area. So can we replace Fx by area with something else? What is force divided by area? Go ahead. Pressure. You had a question before that? Okay. You're Marco, right? You are the one who is going to kick me to the room. Okay. I will remember. So this is external pressure. This is something to keep in mind. And this will become important. We are not talking about the pressure of the gas. This is the pressure that, for example, Marco is applying on me outside. My internal pressure of molecules inside me might be something different. So Px multiplied by ds multiplied by area. ds is the amount by which you move the gas along one direction. It is that tiny little strip that I drew over there. So if you multiply ds with area, it can be written as d volume, right? Change in height multiplied by area is the change in volume of the gas. In other words, delta W is equal to minus Px multiplied by dV. I will call the first law of thermodynamics today as equation number 1, and this one I'm going to call as equation number 2. This is an equation you're going to use a lot during the course of this semester. So what have we written here physically? We have just shown or described that work done on the system. This on is very important. On the system as it expands by a volume dV is delta W is equal to minus Px dV. So let's look at this equation. Let's again consider our system. Something like this. And we have some area A. And we have some external pressure Px that's applying on this system. And in this case, the external pressure, case 1, let's talk about contraction. Okay, the external pressure is trying to contract this system. It's trying to bring it tighter and tighter. In this case, what will be dV? Yeah, you have a question? Sure. Yeah, anytime I go too fast, please stop me. I mean, it would have been fantastic, right? If you could have displayed screen 1 here and screen 2 here. Okay, so when you are compressing a gas, what is dV, positive or negative? Huh? Negative. Anyone thinks it's positive? If you think it's positive, let's chat about it. You're decreasing the volume, right? It's contracting. So dV is negative. In this case, dV is negative. Pressure is always positive. Okay, pressure never becomes negative. Pressure is always positive. It's just a scalar which is applied in one way. So in this case, if I think about minus P external multiplied by dV, this is a negative number. And this is also a negative number. So their product is a positive number. Did I do it right or did I skip something? I skipped the minus in the beginning, right? So minus multiplied by P external. No, yeah, I talked about that. Okay. So minus P external is a negative number. and dV is a negative number. So in other words, work done on system is positive as it contracts. Does this make sense? So what we are saying here, if I had something like this and I'm really trying to contract it, I'm doing positive work on the system. In light of the first law of thermodynamics that says du is equal to delta Q plus delta W, let's say there is no heat in the business. Okay, let's say delta Q is 0 for now. Does it make sense what we just showed here, that work done on the system is positive as I compress it? What do you expect the system to happen when you compress it? Should it heat or cool? It should heat, right? When you take something and make it tighter and tighter and tighter, it heats. And if you think about it, for an ideal gas, we just wrote that U is proportional to temperature. So if delta W is positive, delta U is positive, right? If delta W is positive and delta Q is 0, if delta Q is 0 and delta W is positive, then du is positive, which means temperature goes up. So that makes sense. As you compress a system, as the system contracts, work is done on the system, and generally speaking, its internal energy goes up. This will be true if delta Q is positive, delta Q is 0. If there was something happening with the heat, then this won't apply. But if it was happening in a setup where there is no heat playing a role, this would be true. Let's look at case 2, which is expansion. What will be dV for expansion? I would have expected a more enthusiastic answer. Positive, right? I mean, for contraction, it was negative. We can't make it negative again. So in this case, minus P external multiplied by dV, this whole thing is a negative number. This thing is a positive number. So this whole thing is the product is a negative number. So work done on system is negative as it expands. Does this make sense? So what you're saying is that if the system is expanding, the work done on the system by the surroundings is negative, which means that we are being able to get work out of the system. Can anyone think of a practical, yeah, go ahead.
So the system is basically doing what it wants to. The
Yeah.
system puts pressure on its wall.
Yeah.
And so because the surrounding is resisting the expansion due to the pressure, then the work done by the surroundings is negative.
Yeah. So, but in real life, what is an example of this that we all experience millions of times every second? In fact, we are experiencing it as we are talking, walking. Any idea? Heart or running, right? When you're running, you're walking, anytime the muscles expand and contract, anytime the muscles expand, that's when you are doing work, right? So the fact that when a system expands, that's when you get work out of it. This is also how a steam engine works, right? You have some steam, it expands and it drives something else. So these things are simple, but they invariably confuse people. It's natural to get confused in this. So just follow the convention of how we have written first law of thermodynamics, how we have defined delta Q as heat given to the system and work done as work done on the system. And for expansion work, we showed work done on the system is a minus with P external multiplied by dV. So it's all consistent. Any questions? Okay. So this is all differential work. We want to calculate the total work done on the system as it expands from a certain volume Vi to a second volume Vf. So let's calculate total work done on the system. And I could easily give you a problem where I ask you to calculate the work done by the system. In that case, you can still say consistent with what you have. In the very end, you have to go and put a minus sign. But here we are calculating the work done on the system as it expands from volume VI to VF, some initial volumes to final volume. So W, the work done, will be given as the integral of the differential amount of work, delta W, which itself will be given as VI to VF, P external multiplied by dV. Okay. So let's draw this process. Let's say this is our pressure P and this is our volume V. And we are going from some initial volume VI to some final volume VF. We started at some pressure PI. And let's say the process is such that this pressure is kept constant as we go from an initial volume to a final volume. So this PI is kept the same as some number Px. In general, you could have a procedure where the pressure also changes as a function of how you moved. And since work done is a path function, depending on which path you are taking, they will all contribute different amounts of work, right? That's the tricky thing about work done. But let's say it's a constant external pressure. If Px was constant during this expansion, then W is equal to minus Px can now come outside the integral, right? Because it's a constant number during the expansion process. Vi to Vf dV is equal to minus Px Vf minus Vi. Is this going to be positive or negative? Is Vf more than Vi? Right? And P external pressure is always positive. So minus P external is negative. So negative number multiplied by positive number is a negative number. So work done on the system is negative, which means we were able to get work out of the system, which makes sense, right? Our muscles expanded. We were able to do some work. When you lift a dumbbell or something, right? Your muscles expand, they don't contract, and you're doing work on lifting it. When you are expanding steam, that's when the engine runs, for example. So this means work is obtained from the system during expansion. Okay, that's what we just showed, that work is obtained from the system during expansion. In general, the pressure could change along the path, and it could have looked like the top line over here. It could have looked like the bottom line over here. It could have been anything, and the integral would be complicated. You would have to know exactly what is the framework as per which pressure is changing and then calculate it. So this all looks very abstract. Let's do something. Let's look at an actual chemical reaction and let's calculate these things. That will give you some more intuition. So this is a problem straight out of Atkins. Go ahead.
The work is negative, right? Because you take
Mhm. It is confusing. Once in a while, you will wake up at 3 a.m. and be like, no, 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 negative work. No, what's going on? It's confusing, but just be consistent. Work done on the system being negative means the system is doing work against the surroundings. Okay, let's look at this problem. I want you all to take 2 minutes. I will time it here and try to solve it yourself. Not get the final answer, but try to sketch on your paper, on your note, how would you solve this? Okay, and then we will work through it together. Just take 2 minutes. Okay, let's work through it. Part A. So we have, what do we have here? We have some sort of vessel, and in this vessel, we have 50 grams of iron reacting with hydrochloric acid to produce FeCl2 aqueous, everyone's favorite reaction, and hydrogen, okay? In the first case, the vessel is a closed vessel of fixed volume. In the second case, it is an open beaker at 25 degrees Celsius. So in the first case, it's closed, and in the second case, it's open to the atmosphere. It's closed, its volume cannot change. The reaction is happening inside here. We want to calculate work done over here. What is the formula for work done? Delta W is equal to minus P external dV. What can we say about the work done in the first case? Why? There is no change in volume, right? We don't have to worry about anything. The first case is awesome. 0. Great. Second case is a bit harder. We will have to think carefully. So let's work through it. Atkins, and now this 2.8.1 might change addition to addition. That's why I have in my notes online, you will see the problem pasted. So case A, dV is equal to 0. Therefore, one thing to keep in mind, here we are implicitly assuming that the problem is asking us about expansion work, right? There are other types of work. We will be looking at them in a moment. It's the problem, if it was better stated, we should have stated the expansion work or the pressure volume work. There can easily be other types of work, and we will be looking at them. Case B is a bit harder. Let's work through it. But let's work through it systematically. So we know delta W is equal to minus P external multiplied by change in volume. Okay. So W, the work done, is going to be the integral of this thing minus P external dV and now we are stuck. How should we proceed from here? The hint is it's an open beaker. So what can we say about P external? It's the atmospheric pressure, and unless your reaction is some crazy scientist, Rick and Morty type reaction, creating another universe and the P external is changing, it's probably not going to happen, right? So P external is a constant in this case. So we can bring it outside here, the integral, and write it as dV. Okay. Then this becomes minus P external multiplied by Vf minus Vi. So far, there is no chemistry. In fact, many of you might be like, where is the chemistry in this class? It's zero chemistry. It's all physics and math. Let's look at a bit of chemistry. Let's write down our equation, our reaction. So we have iron solid reacting with hydrochloric acid, which is aqueous, to produce iron chloride, which is also aqueous, plus hydrogen gas. So the reactants are solid and liquid, and the product is liquid and gas. Which has, out of these four things, which one has the highest volume? Hydrogen. How much higher? Like ridiculously higher, right? Hydrogen is the lowest density ever. So the volume of iron solid, that's just a little bit of chips, right? Just a few chips that you have over there, is going to be smaller than the volume of HCl aqueous, which might be similar to the volume of iron chloride aqueous. One of them might be bigger, one of them might be smaller, I don't care. But all of these, which will be way, way smaller than the volume of hydrogen gas. When you do this reaction, you're basically the volume, your beaker better be big. It's a lot of hydrogen that you're producing. Therefore, what equations did we number to? We went to equation 2. Let's call this equation number 3. in equation 3, VF is way more than VI, right? The final volume after this reaction is over is the volume of the hydrogen. And since there was no gas to begin with, if you had a reaction where you had gas to begin with, you won't be able to say this, right? And life would be complicated. Right now, since there was no gas to begin with, there was solid and liquid. Therefore, VF minus VI can be approximated as VF. It's like 0.1 milliliter and 100,000 liters type of difference that we are talking about, kind of, it's huge. So VF minus VI can be written as simply VF. Therefore, W is equal to minus P external, VF minus VI. This is exact, but approximately this is going to be minus P external, VF. We still don't have an answer. We still have to work through it. Now, so here, this was our assumption 1. In the homework problems, there is a problem where I asked you to make your assumptions, state your assumptions, and one of you asked me to get clarification. I don't want to write the whole textbook here. Just say things there. Like, for example, here you're assuming that the gas has a much higher volume than the solid, which is a fair assumption. Now we will make a second assumption that H2 acts as an ideal gas. It's an assumption. It's not as good of an assumption as the first one, but it's an assumption we are going to make in order to proceed further. So that means that W is equal to minus P external can be written as multiplied by V volume, V final volume is minus P external nRT by P external, right? Because we are assuming it is an ideal gas. So V final must be equal to nRT by P external. And this is super nice because now the P external cancels out. You don't even need to know whether your reaction is happening at sea level or it's happening at the top of Mount Everest. It just cancels out the P external. So W is equal to minus nRT. So we are almost there. What is N? N is number, let me write this on next page. Let me give you a moment to catch up with me, then I will move to the next page. Okay. So we just showed that W is equal to minus P external multiplied by final volume is equal to minus P external. This is approximate now. The first one was exact. The second one is approximate using assuming ideal gas is equal to minus nRT. And N is number of moles of hydrogen produced. So we need to calculate that. We are back to some more basic chemistry now. How do we do that? We have been, what information have been given? We have been given number of grams of iron. Okay, so looking at this reaction, how can you connect the number of moles of iron reacting with the number of moles of hydrogen produced? What can we say about that? You're nodding your head in the back. They should be same, right? There is no difference. It's 1:1 ratio. Its moles are conserved. This is number of moles of iron used, and 50 grams iron means 50 gram divided by 55.85. That's the molar weight. So we get something. We get 50 divided by 55.85. You can calculate the precise number. Something smaller than 1. That's the number of moles of hydrogen you produce. Now we can finally calculate our W. W, and let's call this equation number 4. And there we will multiply all the numbers together. Equation number 4 has a minus sign. It has an N. We saw that N is equal to 50 divided by 55.85. multiplied by R, that is 8.3145, multiplied by temperature, which is given as 25 degrees Celsius. So that's 298 Kelvin. By the way, just to state the obvious, in thermodynamics, anytime you see temperature in an ideal gas law or an equation of state, it's always absolute Kelvin, absolute temperature scale, always in Kelvin. You might be given information in Celsius or Fahrenheit or any other temperature scale you fancy. You have to change it to Kelvin. This, if you just multiply things together, comes out to be minus 2.2 kilojoule, or minus 2.2 kilojoule work is done on the system, or system does plus 2.2 kilojoule of work as it expands against the atmosphere. So what this really means is that if you had 50 grams of iron reacting with hydrochloric acid, and it expanded, the expansion could help you move something, right? If you had a heavy weight put over there, this expansion would do work and move this weight. And you can calculate how much work would it do. It would be 2.2 kilojoule, which is really tiny, right? It's half a kilocalorie. It's like, yeah, it's really small, like a cupcake or something has 200 kilocalories weight, right? So it's a half a kilocalorie weight that you're getting out of this process. Very, very small amount of work done. But that's what we had. So this problem, the first part was trivial. She could solve it even without thinking, right? The work done is 0. You had no issues with that. The second part, however, was a bit more complicated. And so your exam problems will often tend to look like this. You have to work through things carefully. You have to think about things systematically, but go over this problem again at home. Make sure you can do it after closing the notes, and it should be obvious. If this is obvious and you get the right sign and everything in the end, and always look for intuition. System is expanding. So work done by the system should be positive. Work done on the system should be negative. Okay, so use these things always to guide yourself. Any questions? Okay, so a very important point to note here is that we are talking about delta W is equal to minus P external multiplied by dV. We are not really talking about the pressure of the system itself. We are talking about the external pressure being experienced by the system. This is not equal to, in general, to the pressure of the system. This brings us to a very important concept, which is the concept of reversible expansion and reversible change. So let's say I had a container. Actually, let me draw it vertical. It's more intuitive. And this was my system. And this was my surrounding. Okay. And the surrounding, we're applying a P external on the system, which was keeping the system a certain way. The system will have some P pressure P. And in this case, P is not equal to P external. You are applying some tight pressure and you are keeping the system. It's not in a state of equilibrium. So if P not equal to P external, let's say if P external is much more than P. So if you reduce the pressure, what would happen in this case? Actually, should I go through? Let's look at this thing from the concept of temperature. It's a bit more intuitive. Let me scratch this. With temperature, it's more intuitive. So let's think about two gases through a container. One is at temperature T1, one is at temperature T2, okay? And I will restart from here next time because this is an intuitive concept, but let's start today again. So, and let's say at equilibrium, we know heat is being exchanged. It's not that heat transfer is not happening, but the amount of heat going to the right is roughly equal to the amount of heat going to the left. So when that happens, we know thermal equilibrium means T1 is equal to T2, right? And there is no net energy movement. So now let's think of a case where T2 is more than T1, but ever so slightly. In this case, what will be the direction of net heat flow? Left to right or right to left? Right to left. T2 is hotter, right? So T2 would be like, okay, I will give you some heat. So on an average, there will be more heat going to the left side. And if I had this way, where this was T1 and this was T2, and T1 was ever so slightly larger than T2, then heat would be going slightly to the right. So the question now is, if I took this case and changed T2, I decreased T2 slightly, it would either become the same as T1. If I decreased it ever so slightly more, it would become smaller than T1, right? If I decrease T2, it would lead to this situation, right? When I decrease T2, since it was ever so slightly larger than T1, it's like a soccer game or a game of tennis or basketball or something going on where the points are just balanced. If you decrease T2, you drift into this situation, and the heat direction, which was going from right to left, goes from left to right. At the same time, you could imagine a process where you had the same T1 and T2, but now T2 was much more than T1, way, way hotter. In this case, what would be the direction of heat change? Again, right to left, right? Because T2 is so much hotter. So the net heat is still going in this direction. Now I decrease T2 slightly. What will be the direction of heat change? It will still be the same, right? Because T1 was 100 Kelvin, T2 was 500 Kelvin. The question is slight change. If you decrease T2 a lot, then T2 can become smaller than T1. But if you decrease T2 slightly, still T2 is going to be much more than T1. So next time, what we will talk about is that this type of change is an example of a reversible change, while this or reversible process, while this over here is an irreversible process, and we will quantify these notations. So this sounds abstract, but this is where we are going to start from next time. Next time, we will also talk about examples of different types of work, not just pressure volume work, but other types of work.